Hi, in this video we're going to look at area and the fundamental theorem of calculus. We're going to use that fundamental theorem of calculus to evaluate a definite integral, and we'll also use the definite integral to find area. The fundamental theorem of calculus says, if a function f is continuous on a closed interval from a to b, and capital F is the antiderivative of that function on the interval from a to b, then the integral of the function with respect to x from a to b is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. So this is our definite integral notation. It looks a lot like our indefinite integral notation, but this time it has that a and b on it. Let's go through the parts of this definite integral. So this is the definite integral, the one that has this a and b on it. What sits inside the definite integral is the integrand. Remember that the integrand is a derivative. The dx is your variable of integration. It tells you what you're integrating with respect to. The a and b, these are your limits of integration. These limits of integration are x values, where x equals a is your smaller value, and x equals b is your larger value. The smaller value is also known as the lower bound, or lower bound limit. The larger value is also known as your upper bound limit. So a is our lower bound and b is our upper bound. Notice that the upper bound b value is on top and the lower bound a value is on the bottom. So let's go see how we use this fundamental theorem of calculus. So the first thing you're going to do is you're going to integrate the function as usual, but do not put plus c on the end. Instead, you're going to put a vertical line to the right of the antiderivative and put the limits of integration, meaning your upper and lower bounds, on it. So, we're starting out with the integral of f of x with respect to x from a to b. This is going to give you some antiderivative, capital F of x. We're not going to put plus c. We're going to draw a vertical line to the right of it, and we're going to put our upper and lower bounds on it. Here's a, lower bound goes on the bottom, b, upper bound goes on top. Then we're going to evaluate the antiderivative at the upper bound limit and subtract the antiderivative evaluated at the lower bound limit. So we're going to take the antiderivative, capital F of x, which we said we're going to evaluate from a to b. But first we're going to start with the antiderivative evaluated at the upper bound, b, and then subtract the antiderivative evaluated at the lower bound, a. And as a little side note, the result of the definite integral is a number. So when you do the f of b minus the f of a, what you're going to get is a number. So we're ready to go do some examples, but before we work on the definite integral, we should probably go back and refresh some of our indefinite integrals. So let's evaluate the indefinite integral of x plus 2 with respect to x. This is the integral of a polynomial function. Please remember, if you have a polynomial function, you're going to integrate each term separately. So that would mean that we're going to integrate x with respect to x, and then add the integral of 2 with respect to x. Remember, we're integrating. So with integration, when you have a variable, you add 1 to the power and divide by the new power. So the antiderivative, this is your capital F of x, is going to be adding 1 to the power. It's going to give us x squared divided by 2. Plus, when we integrate 2, because there is no variable, you're going to keep the 2 and add the variable in, x. This is an indefinite integral, so at the end we put plus c. Let's do another example. This time we're integrating x divided by x squared plus 3 to the 4th power with respect to x. Okay, this time we have a fractional integrand. Notice that in the denominator you have one term being raised to a power, or you have one big parenthesis with the power in the denominator, which means the denominator itself is one term. We're going to bring that denominator to the numerator. And make it to the negative 4th power with respect to x. Now that we're here, we do have a composite function, and we need to make sure that we have what we need to integrate, meaning we need a strategy box. Remember, u is your x squared plus 3, and the derivative of x squared plus 3 is 2x with respect to x. Before I can integrate this function, the integrand needs to have a 2, it needs to have an x, and it needs to have the dx. When I look inside, I can see that I do have the x, and I do have the dx, but I don't have the 2. But that's not a problem. We're going to put the 2 in, and we'll multiply the outside by the reciprocal of 1/2. Remember that when I put something in and multiply on the outside, if I multiply those two things together, they should multiply to positive 1. 1/2 times 2 is positive 1. Now that I have the du parts, and the du parts are right here, what my integrand looks like is 1/2 times the integral of u to the negative 4th power and the du parts. So in order to integrate, we're just going to use the power rule. Power rule again says that we're going to add 1 to the power. Of course, we're going to bring the 1/2 down, right? So 1/2 times adding 1 to that power, u to the negative 4 plus 1. Negative 4 plus 1 is negative 3 power. And then divide by that power of negative 3, and I can add c because we're dealing with an indefinite integral. Now I need to simplify this. So we're going to need to bring the u to the negative 3rd down to make that a positive 3rd power, and we'll multiply these fractions together. This is going to give us 1, or I should say negative 1 over 6u to the positive 3rd power plus c. And this is your antiderivative, but we do need to change this u back into its x squared plus 3 form in order to finish this off. So the antiderivative is negative 1 over 6 times x squared plus 3. Remember that u is being raised to the 3rd power, so the x squared plus 3 is now being raised to the 3rd power plus c. And here's your antiderivative. Let's go do another indefinite integral. Okay, example C. This time let's integrate 3x to the 3rd power divided by x to the 4th plus 2 with respect to x. Again, this time we are integrating a fractional function. However, there are no parentheses in the denominator, so we will put the parentheses in and raise it to the 1st power. so that we can create our strategy box. U is equal to x to the fourth plus 2, and the derivative is equal to 4x to the third with respect to x. We need to see if our integrand has a 4 and x to the third and the dx before we can integrate. Notice that what we have is an x to the third and we have the dx, but we do not have the 4. What we have is a 3. But remember, this 3 is not part of the du parts, so we're going to take the 3 and we're going to move it to the outside of the integrand. Now that we've moved the 3 outside, we still need that 4, so we're going to put the 4 in, but multiply the outside by the 1/4. So here goes the 4 and a 1/4 on the outside. Now remember, if we were to multiply all of this together, the 1/4 times the 4 would be equal to positive 1, and if we multiply the 3 back in, we get the original integrand. Now that I have all of my du parts, I have the 4, the x to the third, and the dx. My integrand is of the form 3/4 is on the outside, and I have in the numerator the derivative parts du, and in the denominator I have the u, but it's being raised to the first power. Please remember that when you see this, your antiderivative is going to be whatever you have on the outside, which is 3/4, times the natural log of the absolute value of u, plus whatever the c is. In order to finish this off, we'll need to replace this u with the value of x to the fourth plus 2. So our antiderivative is 3/4 times the natural log of the absolute value of x to the fourth plus 2 plus our constant c. A couple more examples before we get into the definite integral. In this example, we're going to integrate the indefinite integral e to the 3x times the square root of e to the 3x plus 2 with respect to x. Before I do anything, the first thing I'm going to do is get out of that radical form. Okay, so now that we're out of radical form, we have our parentheses and we can see that we need a strategy box here. So remember, u is the thing that's inside the parentheses. So u is going to be the e to the 3x plus 2. The derivative of e to the 3x plus 2, now this is a polynomial, so we'll go term by term. Remember that exponential functions are also composite. So the derivative of e to the 3x is e to the 3x. However, remember that you must also take the derivative of the exponent. So it's the parentheses go around the exponent. The derivative of that 3x is 3. The derivative of this 2 is 0. So the derivative here is 3e to the 3x power with respect to x. So here's your strategy box. What we need inside of our integrand is we need a 3, we need an e to the 3x power, and we need the dx. What we have is the e to the 3x power, and we have the dx, but we need to get the 3, so we'll put the 3 in, and we'll multiply the outside by the 1/3. And now that we've fixed the integrand, we can see that our integral is in the form of 1/3 times the integral of u to the 1/2 power, and the 3e to the 3x dx, all of that, those are the du parts. So now we can use the power rule in order to integrate. We get 1/3 times. Power rule says we're going to add 1 to that power. So the power right now is 1/2. So when we add 1 to the power, 1/2 plus 1 is going to give us a 3/2 power. We're not going to divide by the fractional power. We're going to multiply by the reciprocal of the fractional power. So that's going to give us 2/3. And now that we're at the end, we're going to put plus c. We're going to clean this up. So this gives us 2/9 u to the 3/2 power plus c. To finish this up, we're going to change this u into its original form of e to the 3x power plus 2, so that our antiderivative is 2/9. The u is e to the 3x power plus 2. This is being raised to a 3/2 power plus c. Okay, let's go to the next example. In our next example, we're going to integrate 5/x with respect to x. So if your integrand ever has a fraction that is some number over x, then you'll pull the number outside the integrand and use the log rule that says when you integrate 1/x, this is equivalent, or this is equal to, the natural log of the absolute value of x plus c. So since our integrand is 5/x, that's a number over x, we're going to pull that 5 to the outside. So it's going to become 5 times the integral of 1/x with respect to x. And so the antiderivative is going to be 5 times the natural log of the absolute value of x plus c. These are very simple to do. You just need to remember. So again, let's say we are integrating 3/x with respect to x, a number over x. The only thing you need to do is pull the number out so that you have just 1/x on the inside, and then your antiderivative is going to be whatever the number is times the natural log of the absolute value of x plus c, and there's the antiderivative. Okay, let's go to the next example. In this example, we're going to integrate e to the 4 minus 5x with respect to x. Please remember that when you have an exponential function, first thing you want to do is put parentheses around the exponent so that you can create your strategy box. In this case, u is going to be your 4 minus 5x. And the derivative of 4 minus 5x is, the derivative of 4 is 0, and the derivative of negative 5x is negative 5 with respect to x. So we need to have a negative 5, and we also need to have the dx inside the integrand. This particular integrand only contains the dx, which means we'll need to put the negative 5 inside and the reciprocal negative 1/5 on the outside. So now that we've put the negative 5 inside, the negative 1/5 outside, our integrand is in the form of negative 1/5 times the integral of e being raised to the u power, and the negative 5 dx, those are the du parts. So the antiderivative is negative 1/5 e to the u plus c. The only thing we need to do is to change the u back into its form of 4 minus 5x. So our antiderivative is negative 1/5 e to the 4 minus 5x plus c. And here's your antiderivative. Okay, so now that we've refreshed what or how to integrate all types of different functions, now we're going to look at integrating or evaluating definite integrals. Let's refresh our memories one more time on what this process is going to look like. So we're first going to integrate the function just like any other function, but we're not going to put plus c on the end. We're going to draw the vertical line and put the limits a and b on that vertical line. And then we're going to evaluate the antiderivative at the upper bound limit b and subtract the antiderivative at the lower bound limit a, and the result will be a number. Okay, let's go do the first definite integral. So now let's evaluate this definite integral of negative 3v plus 4 with respect to v from 2 to 5. The first thing we need to do is integrate. Because this is a polynomial function, we have negative 3v plus 4. This parenthesis doesn't have a power on it, so technically we don't really need the parenthesis. And what you have here is a polynomial. So because it's polynomial, we're going to integrate each term separately. When we integrate negative 3v, we're going to keep the negative 3. And then we'll add 1 to the power of v. So instead of v to the first power, it's going to be v to the second power. And we're going to divide by that power of 2. In the second term, we have a 4. Because there's no variable, to integrate, we're going to add the variable. Now, because this is a definite integral, we're not going to put plus c. We're going to draw the line beside this antiderivative, and we're going to put our limits of integration from 2 to 5. This is your antiderivative. Okay, now that we have the antiderivative, the second thing we want to do is we want to evaluate. We're going to evaluate the antiderivative f, evaluate it at the upper limit, which is 5. And then we're going to subtract the antiderivative at the lower limit, which is 2. We're going to do the f of 5 first. What that means is what we're going to go and in the antiderivative, anywhere there's a v, we're going to replace it with the 5. So this says we have negative 3, instead of the v, we're going to put a 5, which is being squared and divided by 2. And we're going to add the 4, and instead of the v, we'll put the 5 here as well. So this is our f of 5. Now we want to subtract the f of 2. F of 2 means we're going to replace all the v's in that antiderivative with 2. So negative 3 times 2, that's being squared, over 2, plus the 4, replacing that v with 2. And here is our f of 2. Here is our minus, so f of 5 minus the f of 2. Now the only thing we need to do now is just go and finish this up. So this says that we have, and stay inside your square brackets until you have a single result. That's the easiest way to do these. So we have negative 3 and 5 squared is 25. So negative 3 times 25 over 2 plus 4 times 5 is 20. Minus, in the second parenthesis, we have negative 3 times 2 squared. 2 squared is 4. So 3 times 4 over 2 plus 4 times 2 is 8. Continuing to clean this up again. So negative 3 times 25 gives us negative 75 over 2 plus 20 minus, and negative 3 times 4 is negative 12 over 2 plus 8. Okay, so you should reduce your fractions if possible. And if you can't reduce your fractions, then build your whole numbers to fractional form. So in these parentheses, notice that negative 75 over 2 is not going to be reducible. So instead, we're going to build this 20 here so that it is also a fraction with a denominator of 2. To do this, I'm going to multiply this 20 by 2 over 2. So this gives me negative 75 over 2 plus, instead of the 20, so 20 times 2 is 40 over 2. 40 over 2 is still equal to 20. Now, minus, let's look in the second parenthesis. We have a fraction, negative 12 over 2, which will reduce to negative 6 plus the 8. Okay, and so negative 75 over 2 plus 40 over 2 is negative 35 over 2. Minus negative 6 plus 8 is positive 2. Now that we have a single number inside of each of these square brackets, we can drop the square brackets. So negative 35 over 2 minus 2. But now we need to put these two together, and in order to do that, I need to get this whole number into fractional form. So I'm going to multiply it by 2 over 2. This gives me negative 35 over 2 minus 4 over 2. And altogether, this is going to give me negative 39 over 2. And here is the result of the definite integral. Okay, let's go try another example. In this example, we're going to evaluate the definite integral of the quantity of 4t plus 1 being raised to the second power with respect to t from 0 to 1. First, we need to create a strategy box. U is equal to 4t plus 1. The derivative of 4t plus 1 is 4 with respect to t. Before we can integrate, we need to have a 4, and we also need to have the dt. This integrand has the dt, but it doesn't have the 4, but we will just put the 4 in, and we'll multiply the outside by the 1/4. And once we do this, you can see that we're now in the form of 1/4 times the integral of u squared, and the 4 dt, those are the du parts. So now we're going to use the power rule to integrate. So we're going to bring down the 1/4. We started with u to the second power, so using the power rule says we're going to add 1 to the power, so it gives us u to the third, divided by 3. I'm not going to put plus c because this is a definite integral. Instead, I'm going to put the line on the end and put the limits from 0 to 1 on here. I'm going to clean this up a little bit further so that I get u to the third power being divided by 12 from 0 to 1. Okay, so this is my antiderivative. However, the limits that we see here, these limits are in terms of the original variable t. And before we can use them, the antiderivative also needs to be in terms of t. So we need to change this u back into its original form, where u was equal to 4t plus 1. So we rewrite the antiderivative as the u is 4t plus 1 being raised to the third power over 12 from 0 to 1. And now my limits are in terms of t, and my function, that antiderivative, is also in terms of t. So now we can evaluate the f of the upper limit 1 and subtract the f, meaning the antiderivative, at the lower limit 0. Okay, let's do the f of 1 first, meaning, again, we're going to go into this function, the antiderivative, find the t, and replace it with 1. So that's going to give us 4 times 1 plus 1 to the third power being divided by 12. That's your f of 1. And then we're going to subtract the f of 0, which is 4 times 0 plus 1 being raised to the third power and divided by 12. Let's clean up each of these square brackets. In the first one, 4 times 1 is 4, plus 1 to the third power over 12, minus 4 times 0 is 0 plus 1 to the third power over 12. Cleaning up a little bit more, 4 plus 1 is 5 to the third power over 12, minus 0 plus 1 is 1 to the third power over 12. 5 to the third power, so 5 times 5 is 25, and 25 times 5 is 125 over 12, minus, remember 1 to any power is always 1 over 12. Now that we have a single number inside of each of these square brackets, we're going to drop the square brackets, so 125 over 12 minus 1 over 12 is equal to 125 minus 1 is 124 over 12. Remember that we're dealing with fractional numbers, and you must reduce if possible. So we have 124 divided by 12, and there's a common factor of 4 in both. So 124 divided by 4 is 31, and 12 divided by 4 is 3. And here is the result of that definite integral. Okay, so let's move to the next example. So in this example, we're going to integrate the definite integral of negative 3 times the square root of x with respect to x from 1 to 4. First thing we need to do is change that radical into its exponential form. Okay, so this is not a composite function, so I don't need a strategy box, but I do need to use the power rule in order to integrate. So I'm going to keep the number negative 3, and now I'm going to add 1 to the power. So right now the power is 1/2. And when I add 1, I'm going to get a new power of 3/2. So we have x to the 3/2 power, and because this power is fractional, I'm not going to divide by 3/2. I'm going to multiply by the reciprocal, which is 2/3. Now, again, this is a definite integral, so let's draw the line to the side and put the limits of integration on it, 1 and 4. Let's clean this up a little bit. Negative 3 times 2/3, when I when I simplify this, The 3's are going to cancel, so what I'm left with is negative 2x to the 3/2 power being evaluated from 1 to 4. So now we're going to evaluate the f of 4 and subtract from that the f of 1. So we're going to do the f of 4 first. Of course, what that means is we're going to replace this x in the antiderivative with a 4. So we have negative 2 times 4 being raised to the 3/2 power minus the f of 1. Replacing the x with a 1. So negative 2 times 1 to the 3/2 power. So now we need to simplify each of these square brackets. And so I want to remind you that 4 to a 3/2 power is the same thing. Remember, a fractional power is a radical, right? So this is the square root of 4 being raised to a 3rd power, which means we have the square root of 4 is 2 being raised to the 3rd power, and this is the same thing. 2 to the 3rd power is 8. So then we have negative 2, and the 4 to the 3/2 power is the same thing as 8 minus negative 2. Remember that 1 being raised to any power is always just 1. It doesn't matter if it's a fractional power or a whole power. 1 to a power is just 1. So let's finish cleaning this up. So in the first one, we have negative 2 times 8. That's a negative 16. Minus negative 2 times 1 is a negative 2. Single numbers inside each one, so we'll drop the parentheses. So we have negative 16. But minus 2 is plus 2. And negative 16 plus 2 is negative 14. And here's the result of this definite integral. Let's move to the next example. In this example, we're going to evaluate the definite integral of e to the 2x with respect to x from 0 to 3. Since we're looking at an exponential function, we're going to put the exponent in parentheses so that we can create our strategy box. U is equal to 2x. The derivative of 2x is 2 with respect to x. The integrand needs to have the 2 and it needs to have the dx before we integrate. Since we only have the dx, we're going to need to put the 2 in and multiply the outside by 1/2. Now we're in the form of 1/2 e to the u and the 2 dx. Those are the du parts. We're ready to integrate. This becomes 1/2 e to the u, not a definite integral. It's not an indefinite integral. So we're going to put our line down the side and put our limits 0, 3 on it. Again, let's return this u to its original form, which was 2x. So our antiderivative becomes 1/2 e to the 2x power, and we'll evaluate this antiderivative from 0 to 3. F of 3 first means we're going to replace the x in the antiderivative with 3. So we get 1/2 e to the 2 times 3 minus, when we do the f of 0, we're going to have 1/2 e to the 2 times 0. Cleaning these up, we get 1/2 e to the 6th power minus 1/2 e to the 0 power. Okay, remember that anything to the 0 power is equal to 1. So we have 1/2 e to the 6th minus 1/2 times 1. Okay, I'm going to drop these. 1/2 e to the 6th power minus 1/2 times 1 is just 1/2. And now I'm going to evaluate this. Now, remember that e is a number, which is approximately 2.71828. Remember, it's this long decimal digit that doesn't stop. So in order to evaluate this, you will need to use a calculator. So if I ask you to approximate to 2 decimal digits, what you will get is 201.214. But again, I only want it to 2 decimal places, so I want to stop at the second one. Of course, in order to do this, I have to evaluate this number here. So if I want it to 2 decimal places, remember that if the third number is 5 or more, then you'll move that last digit 1 up. If it's less than 5, you stay where you are. Since 4 is less than 5, my approximation is 201.21. And again, if that number was 201.215, then my approximation would be 201.22. Okay, let's move to the next example. In this example, we're going to evaluate 1 over x with respect to x from 1 to 2. Remember that anytime you evaluate or anytime you're integrating 1 over x, the antiderivative is always the natural log of the absolute value of x. And if it's a definite integral, as we have here, you're going to evaluate this over the limits, this time from 1 to 2. This means we're going to evaluate this antiderivative at 2 and subtract this antiderivative at 1. So for the f of 2, we have the natural log of the absolute value of 2 minus the f of 1 says we have the natural log of the absolute value of 1. Now, I want you to recall from your log properties that if you have the natural log of 1, that this is equal to 0. So this bracket will be equal to 0. That leaves us to evaluate the natural log of the absolute value of 2. And again, this is not something we can do without that calculator. So, plugging this into the calculator, you're going to find that it is approximately 0.693. And again, if I ask you to round this to 2 decimal places, remember you're going to use this third place to help us do that. So because the third place is less than 5, then our answer to 2 decimal places is 0.69. Okay, let's go talk about area. So we can use a definite integral to find area under a curve. So area is equal to the definite integral of f of x with respect to x from a to b, which means that to find the area, then we're just going to evaluate the f of b minus the f of a. Now, we know when we do a definite integral, what we find is a number. When you're finding area, remember that area must be a positive value. So if your value is negative, that means something went wrong and you need to go back and figure out what you did wrong, because it has to be a positive number. So to find the area under the curve, you're going to integrate the function over the x values. That means you're going to put the function inside the integrand, and you'll put the x values as your limits. Remember, the smaller limit goes on the bottom and the larger limit goes on the top. Then evaluate the antiderivative over those x values. So the area will be the antiderivative evaluated at b minus the antiderivative evaluated at a. So let's find the area of this region. This region is your y equals x plus 2 divided by x. The region is going over the x values from 2 to 4. The first thing we're going to do is set up this integral. So area is equal to, remember, you're going to set up the integral, put your function inside, which is x plus 2 over x, over the x values. So the x values are going from 2 to 4. And so the smaller number goes on the bottom and the larger number goes on the top. And this we are going to be integrating with respect to the variable x. The first thing I notice is that we are integrating a fractional form. Because I have a polynomial, I am going to simplify this. Remember, you don't want to bring it up, but we will use short division to simplify into a polynomial. So area will be equal to the x divided by the x plus the 2 divided by the x with respect to x. Cleaning this up a little bit more, says that the area will be equal to 1 plus 2 over x. Again, you do not want to bring up the x to the first power. You leave it here. All right, so we have two terms, and because one of them is fractional, I am going to split this up term by term. So that area will become integrating 1 with respect to x from 2 to 4 plus integrating 2 over x with respect to x from 2 to 4. When we integrate the first term, 1, we keep the 1 because there's no variable. We're going to add the variable to the end of it. Remember, we're going to evaluate this from 2 to 4. Plus, with the second one, what we have is a number over x. Remember, when you have a number over x, you're simply going to take the number and pull it to the outside, so that what you get is 2 times the integral of 1 over x. And remember the reason you're doing that, so that you can know the answer is going to be 2 times the natural log of the absolute value of x. And this we're going to evaluate from 2 to 4. Now, you can evaluate each term separately, or you can evaluate them together, meaning I have x from 2 to 4, plus I have the 2 natural log of x from 2 to 4, so I can put them together and just do the whole thing from 2 to 4. Okay, so now we want to do the evaluation. So we're going to evaluate the f of 4 minus the f of 2. So area is equal to f of 4 first, means we're going to go and replace the x's with a 4. So I get 4 plus 2, natural log of the absolute value of 4, minus the f of 2, says I have 2, plus 2, natural log of the absolute value of 2. Cleaning this up a little more, says that the area is equal to 4 plus 2 times the natural log of 4 is something that we'll have to do on our calculator. And we get 6.77 when we round this to 2 decimal places, minus 2 plus 2 natural log of 2 in the calculator is 3.39 when we round this to 2 decimal places. Cleaning up this area, we have 6.77 minus 3.39 to find that the area is about 3.38 square units. Okay, let's talk about using a definite integral to find marginal profit. So the marginal profit for a product is modeled by the derivative of the profit with respect to x is negative 0.0005x plus 12.2. Let's find the change in the profit when the sales increase from 100 to 110 units. To find the change in profit, we're going to need to integrate the derivative. So they're giving us a derivative. It says the derivative of p, dp over dx, says we have the derivative of p, meaning the profit. We have the derivative of the profit with respect to x. So to get back to the profit function, we're going to need to integrate the derivative and then we can evaluate it from 100 to 110. So then I'm going to, again, integrate the derivative function. So that would be the derivative of p with respect to x from 100 to 110. And this is equivalent to integrating the derivative function, which is negative 0.0005x plus 12.2 with respect to x from 100 to 110. So this is a polynomial function, so we'll integrate each term separately. The first term, when we integrate, is going to be negative 0.0005. Integrating the x becomes x squared over 2. Plus, integrating the 12.2 becomes 12.2x when we integrate. And then we're going to evaluate this from 100 to 110. Cleaning that up just a little bit, this becomes negative 0.00025 x squared plus 12.2x being evaluated from 100 to 110. Now we can evaluate this antiderivative at 110 and subtract this antiderivative at 100. So 110 first. This gives negative 0.00025 times 110 being squared plus 12.2 times 110. That's our f of 110 minus the f of 100, just replacing the x's with 100. So here's our f of 110 minus our f of 100. And now using our calculators to help us figure out what this is equal to, says that we're going to have in this first square bracket, we get 1338.98 minus in the second bracket, we're going to get 1217.50. And cleaning this up, we find that the change in profit is going to be $121.48. So this ends the lesson on the fundamental theorem of calculus and area under a curve.